Thank you so much. Thank you so much to the organizer for organizing this conference and for inviting me to speak. So this talk that I will discuss today is joint work with Daniele Alessandrini, Nicolas Tholozan, and Anna Wienhard. I went back and forth between chalk talk and slide talk, so I'll probably do a mix. So, okay, so what we will do is Tangrin basically cover most of my background, so thank you so much. I will just review, but you guys now are expert on everything needed. But yeah, I'll start with the motivation from the low-dimensional case, so where I come from in grad school, then what I'm trying to learn, like this higher type Muller theory and Anosov representation, and then we will discuss our main result. So basically what we are going to discuss is the fact that if you take a connected component of Anosov representation, where you can continuously deform to a Fuchsian representation, then there are domain of discontinuity associated to them, and if this domain of discontinuity is non-empty, you can ask what is the quotient of this domain of discontinuity, and we answer that is a fiber bundle over a surface. And in one particular case, we will discuss the fiber, and hopefully that example will be also a good motivation if tomorrow you will see the discussion of domain of discontinuity in general. I think is a good example to keep in mind, and I'll tell you maybe some question that we have been thinking about or things related. Please stop me at any time if you have any question. Okay, so S for us will be close orientable or oriented in case genus greater or equal to surface. So Fuchsian representation are representation from the fundamental group into PSL2R, which are injective and such that the image is a discrete subgroup. You can look at this action, the action of those representation on H2, and then the quotient gives you back your surface. And so the moduli space of those, you can take all of those discrete and faithful representation up to conjugation, and this is in bijection with marked hyperbolic structure on the surface. Okay, there are many other identification you can have, but there is this nice subset of representation in the character variety that has some nice associated geometric structures. And this is a connected component in the character variety. I want to talk about another space that I really like, and these come from the fact that you can embed the PSL2R inside PSL2C, so isometry of H3, and so then you can take a Fuchsian representation and look what happened when you look at the quotient of this Fuchsian representation in H3. So what happened is that those representations preserve your H2 inside H3, and in fact, they also preserve all the equidistant plane. And so if you are studying the topology, what you get is that you get a surface for every equidistance planes. And so what you get is a tree manifold that is homeomorphic to S times R. And you can ask, can I deform by keeping the geometry the same? And the answer is yes. And so this is this notion of quasi-Fuchsian representation. So those are discrete representation for which the limit set, okay, it might not be a circle, but it still remain topologically a circle, a Jordan curve. And this representation, there are many ways to define quasi-Fuchsian. Okay, I gave you one. They are also quasi-conformal deformation of Fuchsian representation. But the These representation, they also describe a nice subset in the character variety, and when you look at the quotient of H3, you still have a 3 manifold that is homeomorphic to sigma times R, but you also have more geometric structure associated, because your limit set split CP1 into 2 topological disks, and you can take the quotient of those components, and so these quotient give you this disjoint union of 2 surfaces, which in fact they have CP1 structure, complex relative structure on them. It's not obvious, but in this case, so the complement of the limit set is the maximal open set where the action is proper discontinuous on CP1. We will see that when we go to higher rank, where we try to generalize this picture, well, we have to remove more than the limit set, and there might be various ways or various spaces where we'll have to do that. So this is maybe one picture to keep in mind. Okay, so now another piece of the background is like, okay, these are just some nice feature of Teichmüller space. Teichmüller space is a ball. The mapping class group, so the group of orientation preserving homeomorphism up to homotopy act nicely on Teichmüller space. You have a metric on Teichmüller space. So the way I described it before, I kept calling space okay, I describe it just set-wise. When you look inside the character variety, these give you a topology, but in fact you have more. You have a metric structure, and you have much more structure than I will discuss today, but you have this nice mapping class group invariant metric. You have a nice compactification of Teichmüller space, and you have the color lemma. So one question that one can ask is that, okay, so what if we replace the target space, PSL2R or PSL2C, with the group of higher rank? Can we still find connected components in the character variety that are all made of discrete and faithful representation, and that they still keep some of the nice feature of Teichmüller space? And so we can take these as the working definition of a higher Teichmüller space. And so the answer is yes. We have seen some example today. So Tengrin already introduced each representation. I'm going to redefine them in the next slide. And so each defined is a nice subset of the character variety, and Labouri with the notion of Anosov representation, and Fock and Goncharov with the notion of positive representation. They show that these are examples of higher Teichmüller spaces, and then one can define many more. So maxima representation is done by Burge, Iozzi, Wienhard, Burge, Iozzi, Labouri, and Wienhard, and positive representation, and now theta positive representation. So there are many examples, and as Tengrin described today, okay, so this is not the way that Itchin defined this representation. I think is a easier way, at least for me, is like what you do is that you look at the irreducible representation of PSL2R inside PSL-DR. You take a Fuchsian representation in PSL2R, and then you embed PSL2R inside PSL-DR. And these give you a notion of Fuchsian representation in groups of higher rank. And then you can look at all the possible continuous deformation of this representation. So this is a connected component by definition. But the theorem is that all the representation in this component have very nice geometric property. And if some of the nice feature that we have seen before of for Teichmuller space, well, you might say maybe they weren't randomly chosen, but so they are true in the Hitchin component setting, and in fact in much more generality. Okay, I'm just using the Hitchin setting as just one working example. So the Hitchin component is a ball now in a bigger space. And yeah, this is Hitchin and Bonahon-Dreyer. The mapping class group acts nicely on this component. This is Francois. And you can compactify the Hitchin component like Anne Parot did that. And there are many more now, compactification and discussion of that. And there are some nice examples of metric on this space. You will hear one, I think, discussion. I don't see the speaker, but yeah, Carvajales will discuss, I think, the Thurston metric, his work with Dye, Pozzetti, and Wienhard, and then there is the Weil-Peterson metric, so the work of Bridgman, Canary, Labourier, Sambarino, and independently in the case n equal 3 by Chonling. And then Li and Zhang, they have the color lemma in that setting. So in some sense, we have this nice set of representation. They are a connected component of all discrete and faithful, and they have some nice property. On the other hand, I spent some time convincing you that actually quasi-Fuchsian space was also a nice set of representation. The problem is that this quasi-Fuchsian space is open, but is not closed. So it's not a whole connected component. And in fact, in the character variety, in the same component where you have quasi-Fuchsian space, you also can continuously deform to the trivial representation. So it's not a higher Teichmuller space, but it's still a good subset of nice representation. And the link is this notion of Anosov representation. So we want to use the notion of Anosov representation to detect what I call nice representation of the character variety. And yeah, again, now you're all expert. Thanking Eve did such a good job. And so again, I also I wrote the definition in one particular setting, and then we will see a comment that is generalized. But yeah, so we define, I define Borel-Anosov. So Borel is the minimal parabolic. So you can think for PGL, you can think upper triangular matrices. These are representation for which you have a nice limit map. So a row equivariant map from the boundary of your group, the circle in this case, into the full flag that is continuous, transverse, and that has this strongly dynamics preserving property that Tengrin discussed. Any question? Okay, so, and yeah, so as we discussed already, this is just a particular case. Well, you can generalize the group as well, not just by one of S, but word hyperbolic group. You can generalize the target space. You can generalize the parabolic that you take. Okay, so now the question that we will focus on today is, can we interpret this nice connected component as geometric structures? And the answer is yes. So thanks to the work of Guichard and Wiener, Kapovic, Lieb, and Porti, they show that you there is a notion of domain of discontinuity. So, okay, so where this domain of discontinuity live? If you start with the P Anosov representation, you have a limit map in G mod P, this partial flag space. This domain of discontinuity do not necessarily live in the same space. You might change your space, but you have some domain of discontinuity. I think it's hard in general to see when these domain of discontinuity are non-empty, but when they are non-empty, then you can take the quotient, and this domain of discontinuity or their quotient, they come with a natural Gx structure, where G is your group and X is the partial flag space where the domain of discontinuity lives. Okay, so then, well, they answer. So what is left to do is like, well, what we discuss here is like, what can we say about the topology of this quotient? So there has been, so few cases have been discussed, and so the topology was known. And then I think Guichard and Wienhard, and in another paper, Andy and David Dumas, Andy Sanders and David Dumas, they had the conjecture that these quotients were always bundled over the surface. Let's start for today. I think we will discuss the surface group case. Our theorem is a little more general, but so yeah, I think the first theorem that I'll discuss is the fact that if you have a connected component of Anosov representation where you have a Fuchsian representation inside, you can think of this Fuchsian representation as a choice of embedding SL2R in your group. Then, like, take a domain of discontinuity that is non-empty, then every representation there, like it give you the quotient of this non-empty domain of discontinuity is a smooth fiber bundle over the surface. So what is really crucial that I think I didn't emphasize, yeah?
I just want to make, we've been talking about Zariski dense things this whole time, so I just want to point out that this is not Zariski dense, even though it's being Anosov.
Thank you. Any question? Any other question? So I didn't emphasize before, but it's really crucial for our theorem that these domain of discontinuity are co-compact. So co-compact means the quotient is compact. And in order to have the fact that these domain of discontinuity are constant on the connected component, we use these crucially. So I apologize. And Colin Davalo has a very nice independent result, different method. He obtains very similar results with different method. And he has somehow a more concrete construction, but maybe he has to exclude a few cases. But yeah, we are just talking. It will be nice to see the connection between the two work.
Sarah?
Yes?
So your result is about any G, any group G?
Yeah, any group G. Yeah, so one might ask, okay, so these containing Fuchsian representation, do you really need, or how restrictive that is? Well, there are examples of Anosov representation that do not contain Fuchsian representation. Our theorem says nothing about those components, but somehow those components are known to exist in a very few cases.
So in the case of Fuchsian representation is something that factors in some SL2 and the SL2 is
exactly.
Just any SL2.
Any SL2. But already in isometry group of H4, if you remove the containing a Fuchsian representation, our theorem is not true. So there are examples of quasi-Fuchsian representation in that setting, where the limit set is a wild knot and those are not bundled over the surface. Okay, so maybe these can be improved, but
this does not apply to this bubble representation.
Yeah, it does.
It does?
Yeah, it does. So the fiber might be different. And in fact, one comment I was going to make, but maybe I make it now, is that I was the question that we were saying before about distinguishing connected component. It will be interesting to see if the topology of the domain of discontinuity can help in that. Because even if you think of Itchin and Barbeau in SL, let's say 3R, if you look inside the SL3C, it's not obvious, or at least not obvious to me, that those might be connected or might not be connected. And so now Nicolas was just visiting, and with Filippo we are just looking, trying to see if we can study the fiber and see that the topology is different. That would give a way. Yeah. But unfortunately, the fiber in general seems hard to know. Our theorem doesn't give a general, it doesn't tell you anything about the topology of the fiber in general. And we will see that our second theorem is doing one particular case, and we will go through that in details. But maybe I wanted to underline previous results. Hopefully I covered them all, and if not, I apologize. But I think Guichard and Wienhard were probably among the first to really study the topology when G was PSL 4R or PSP 4R, and they look at the domain of discontinuity in projective space. And Alessandrini, Lee, and Schaffhauser, maybe I mispronounced, but they look at the case, I think they look at triangle group in that case, not surface group. And then again, Olivier and Anna, Guichard and Wienhard, they look at PSP in general, again in the projective space. Collier, Tholozan, and Toulis, they have different method. They study SO2n into this photon space, totally isotropic plane inside R2n or R2n plus 1. David Dumas and Andy Sanders, they look at the SL3C case, and they look at the domain of discontinuity in the full flag. And Alessandrini, Davalo, and Lee, they look at the general SLN and again the projective space.
We don't get smooth fibers.
Okay, you don't? Okay.
No, it's a singular. It has singular fibers.
Yeah. So in fact, I think I think your fiber is similar to the construction that we will discuss today. I don't think you guys know the topology of the fiber.
No, we don't.
You know the you know
we
the homology, and you know it's but so in general, the topology of the fiber is hard to calculate, and so what we can do is that in one case, so in the case of SP4C, when you look at the irreducible Fuchsian representation, and we look at the domain of discontinuity in the Lagrangian of C4, we we know the fiber, the homeomorphism type of the fiber. Well, this fiber is dimension 4. You maybe are not surprised by that. Yes, we are using the classification of smooth for manifold. And the way that we prove this theorem is very indirect. So we build another fibration that is not smooth, but that is much more concrete, and so that we can study the homology, we can study the intersection form, and then we use the classification of for manifold to conclude. I put here a question. I was talking with some friends that they do for manifold, and so they were asking me, is F diffeomorphic to this? And he's like, I don't know, maybe. And so apparently there are no known exotic structure on CP2 connected bars, connected some CP2 bar. So I think answering this question would be interesting either way. Well, one will improve our result, the other will maybe be even more interesting, but we don't know yet. I guess there are some sub-cases if our fiber we know a little more of the structure, but we are just looking.
So
Yes. Where CP2 connected some CP2 bar.
What is CP2 bar?
What is CP2 bar? You will see soon.
Okay.
I'm not sure. I'm not sure our result will be very satisfying, because what we do is that we study this other fiber and then we calculate the intersection form. The intersection.
I'm not sure you answering my question. My question is what is CP2 bar? What is it?
Oh, is opposite orientation. Yeah, and this for manifold is very interesting for manifold people. It comes as resolution of singularity. So another question would be, can you see this construction in a much more general setting? Yeah, that is very interesting. We are asking, like right now, it really comes from looking at the intersection form. So yeah, thank you. Any other question? Yeah.
When we deform the representation, it just the manifold deforms continuously.
Yeah, so the topology of the manifold is constant because these domain of discontinuity are co-compact. Yeah, it's not obvious, and we are just studying the fiber at those special points, the Fuchsian point, and then we use Harassman type principle that you know that this topology doesn't change. Yeah.
So ultimately, these questions are just about the Fuchsian.
Yes. Yes. Yeah. And that's also tells you why when you don't have Fuchsian, we don't know. Yeah. You will see, I think, in maybe 1 or 2 slides, like we really study Fuchsian. And in fact, one question that I had later is exactly, even just quasi-Fuchsian, how much can we see maybe the quasi-Fuchsian, not just the Fuchsian? And yeah, I'll be happy to discuss more. Yeah. Okay, so again, maybe just, yeah, I think, yeah, so the first comment for theorem 1 is that, yeah, the topology of those domain of discontinuity is constant. We study at Fuchsian representation, and then that suffice, again, because of the co-compactness. So that's crucial.
Diffeomorphism type is constant, or just the whole
okay, I don't know. Yeah, I think I don't know. It might.
Stratum, isn't it just a response theorem?
I was thinking yes, but now that like I don't know, for the diffeomorphism, I think we already thought. To be honest, we already thought that our theorem would give the diffeomorphism, and then we were wrong. Yeah, so I'm not sure, but yeah.
But either way, I mean, the diffeomorphism type of the whole thing, I mean, the fiber could change its induced structure if it moves around too wildly.
Yeah. And so you see that the main theorem that actually we prove, yeah, this was something that Nicolas really observed, is that when you have a manifold with the proper action of PSL2R, then you have a map into H2, which is PSL2R equivariant and is a locally trivial fibration. This proof uses the notion of a barycenter of a finite measure of compact support on H2. And so you might guess that, in fact, this theorem is more general. So you can replace PSL2R with, maybe I have it here, yeah, so with another semi-sample group of rank 1 with finite center and like H2 with this symmetric space. But yeah, today we will just discuss that. But because, yeah, I didn't write rank 1. Yeah. Yeah, well, our theorem, yes, we like it applies to gamma that is a fundamental group of like, yeah, rank 1, because we really need, yeah, for that theorem we need rank 1, because I didn't write, I apologize, but because we really use the negative curvature to really see that this barycenter, you have this unique minimum. Yeah. Okay, so theorem 2, okay, I just, maybe I already gave you the snapshot, but yeah, so what we are going to do, we have this non-smooth fibration that we build very concretely. I'll tell you in a second where it's coming from. We study its fiber. The fiber that we get is not a manifold, is not even an orbifold, is this bad space, but yeah, exactly, but is concrete enough that what we need to know, that is its homology and this intersection form, we can calculate and then use the classification of four manifold. Okay, so where is this other fibration coming from? We work really hard to get one before. So this non-smooth fibration comes from, like it came, we realized when we were studying the SL2C orbit on Lagrangian of C4. So when we were so first we were studying the sp4r orbits that were already known, and we were trying to understand the topology of each piece. And then when you understand that, but then you try to put things together, and they didn't work really so well. So we studied the SL2C orbit, and we realized that the open orbit there can really be seen as ideal regular hyperbolic tetrahedra, and regular means maximal volume, and the degeneration of that can really be seen as the degeneration of these tetrahedra. So these tetrahedra are fat, are maximal volume, so they can only degenerate to lines or to points. And then what we need to do is that we really need to study these where things collapse, which is where things becomes harder. Okay, so we'll go into the details of this construction. Maybe it's just some background. When you want to think about the reducible representation, the way to think is to think of C4 as homogeneous polynomials of degree 3 in the two variable, and you can define a symplectic structure concretely, where in this case you pair x3 and y3 as 1 and x square y and xy square as minus 1/3. So this formula is just it works in general, and the symplectic group in this case is exactly sp4c. So the Lagrangian subspace are, so isotropic in general is the notion of L contained in L orthogonal, and the Lagrangian is the maximal isotropic subspace, so is where this is inequality. With this setting, we can also really write the limit map that until now we just discuss them as existence, as some magic objects, but in this case the limit map are very concrete. They are the Veronese embedding, and they are mapped, okay, from RP1 into projective space, or from RP1 into the Lagrangian. And so in terms of polynomial, how can we think? You can take a root, a point in RP1, and you can send this point into the polynomial that has this root as a triple root. And so this is a point in projective space when you identify C4 as C3 xy. And the two-dimensional map is you map this root into the span of this first line that we have, and then the polynomial that has like this root as a double root and whatever else you want to put. So the two-dimensional space is exactly the Lagrangian, the two-dimensional subspace where they have this root as a double root. Okay?
Sorry, can I ask a question?
Yeah.
Would you say, is this somehow at the heart of why when you take derivatives, things tend to vanish at the Fuchsian locus because you have a power here in the Veronese map? like, think about like Hausdorff dimensional limit set. You take its first derivative in quasi-Fuchsian space at Fuchsian and it's 0.
Sure. Yeah.
It's more close to saying variance of the Fuchsian because of the contrarian. That's really where it comes from. Right? Maybe it's
Yeah, I think it's
exactly.
pretty much the same. Pretty much the same thing.
Thank you for the comment. But yeah, so this map we can then extend. So this, as using this definition, as map from CP1, exactly the same. Where instead of taking a real root, you take a complex root. Okay, so now I'll discuss this SL2C orbit, and I'm writing it here because then we will discuss the proof of that. So the SL2C orbit on Lagrangian subspace. So what do we have? We have an open orbit. We have a closed orbit, and we have an orbit that is not open nor closed. So the closed orbit is C2C of CP1. So the map that we had before, so maybe C1, C or R. So those were those maps. The middle orbit is what I call KCC minus this. And so how we define this K-space? So this KCC is defined as the union over all points in CP1 of KC C of T. And KL is the set of Lagrangian that contain L when L is a point in CP1. Whoop, CP3. And the open orbit is everything except this. And what I think is really nice, or at least what is crucial for our theorem, I like this geometric interpretation, is that these you can identify with this set of ideal regular hyperbolic tetrahedra. And these other two you can identify as the degeneration of these, and the degeneration of these is just CP1 times CP1. Is not obvious. I'll discuss where tetrahedra comes into play, but these are also not labeled tetrahedra, and this is where the problems come. Is that we have this action of A4 on these 4 points. Okay, so how this proof goes. So I'll discuss. Basically, I'll discuss these two identification, and while we do that, I can even show you these as certain representative here, so like really the orbit of certain points, certain Lagrangian. So the first things to observe is that every Lagrangian in C4 always contain a point that has a double root. Okay, again, not obvious, but you just write in the symplectic structure, and you really see what does it mean to be Lagrangian. Once you know that, you can use the action of SL2C to choose this double root to be 0 and the single root to be infinity. And so you can suppose that the point in your Lagrangian is x squared y. Then you study all the Lagrangian that contain this point, this x squared y. This is a CP1, and so again you can write it concretely. What does it mean to be Lagrangian and to contain this point? And we can use the last remaining freedom of this action of SL2 to really see that this orbit, this one representative here is exactly the span of x squared y and x cube plus y cube. And then what you do is that you just study this Lagrangian. You take the generic element in this Lagrangian. This is a degree 3 polynomial. And you ask how many points with the double root you have. This is a calculation that you can do with the notion of discriminant. Don't ask me to write it down, the formula for the discriminant. I can't do that, but you can really do the calculation. And you really see that there are four, I don't know, V0, V1, V2, V3. These are the double root. And you have, these are the single root. These are 4 points in CP1, so the first things you do is that calculate the cross ratio of these 4 points, and we were very surprised when the cross ratio that came is the most symmetric cross ratio that can come, which is 1 minus I square root of 3 over 2, which is really the cross ratio of tetrahedra that are regular. And same if you do for double root, if you do for single root, and in fact these two tetrahedra are really one the dual of the other. But yeah, it would be interesting, like I don't know, it was not the fact that we expected, but yeah, this is where tetrahedra comes into play. Yeah, so what about this degeneration? For this degeneration, we can really write it down, the homeomorphism concretely, and plus one observation. So this set, by definition, is the set of all Lagrangian that contain a polynomial with the triple root. Then you can really do a calculation with the symplectic structure, the symplectic form, and see that that these actually coincide with the Lagrangian that have a common root. Okay, and in fact this is what distinguishes these two cases. So here one representative is this, and here one representative is this. And so really you write a map from CP1 into this space, where if the two roots are the same, you map into the image under C2 of C, and if they are distinct, you map into the span of the C1 of C, so the polynomial with that root as a triple root, and the one that has this as a single root, and the second as a double root. And this CP1 is what play the role of your degenerate barycenter. Because these tetrahedra, like they can either degenerate where 3 points goes to 1 or everything goes to 1. And so the first factor of this parametrization is what capture this barycenter, is this a common root that we have here. And why this is interesting is because our K C1R which is what we were interested at the beginning. I'll say in the next slide, but this is the set that we need to remove to get a domain of discontinuity in the Lagrangian. This is, in that parametrization, is RP1 cross CP1. Like all the degenerate tetrahedra where the degenerate barycenter lies on RP1. So, okay, so now we know actually how to study this representation very concretely. Because given a Fuchsian representation, then the limit curve is really really given by this Veronese embedding,
so the CP1 is the Schubert variety you're removing at every point along the set.
Yeah. If you want to sound more fancy, that's the way.
You know me. I don't understand math unless I turn it into categories here.
So from our theorem, like taught as tetrahedra or degenerate tetrahedra, you have this map into the barycenter or the degenerate barycenter. So you have a map into H3 union CP1, and the fact is that the domain of discontinuity, which is exactly the complement of this set here, then maps into H3 union CP1 minus RP1. And so now what we are going to do is that we are just projecting everything down to H2. Okay, so this is this non-smooth map from the domain of discontinuity into H2. Okay, so now we need to study the fiber. So what is the fiber? The fiber is take a point in H2, take the preimage under this projection. This is like if we take 0, then you can take the geodesic between minus I and I. And so you look at all the regular ideal hyperbolic tetrahedra with barycenter or degenerate barycenter on this line. So this fiber, our fiber, has a nice projection into the unit interval, and we understand what happened at an interior point because this is a very known cipher fiber space. This is SO3 mod A4. This A4 is really what gives the trouble, and this A4 is because our tetrahedra, they don't come as with an order. This and so this you can see as in some sense. So these really correspond to the unit tangent bundle orbifold of S2, 2, 3, 3. And in fact, these singular fiber here, these circles, these families, have a nice interpretation. So they are the tetrahedra with or the order 3 symmetry or the order 2 symmetry. But what is the problem is that at the extreme, everything crashes into a sphere. And in fact, in the sphere, we have two special points, the point minus I and I, or, well, I think maybe here we have I and I minus I. And so these are the points that will give singularities. And so, okay, so maybe like, okay, what do we have? So we have our smooth projection, and these, I think I call it P, these give a fiber FP, and then we have this non-smooth projection, this one coming from tetrahedra, and these give you another fiber. But these fiber are homotopic equivalent, and so if we want to study these, we can study this concrete case. And so, okay, maybe this is now might not mean much to you, but you can really calculate the homology. How you do is that you can really write this F as A union B, and you can look what is the intersection between A and B. So this fiber has a nice involution, which is what tells us that the intersection form is a signature 0 and is indefinite. So A is this part, B is this part, and Y is exactly this space. And so we can really write it down, the homology, concretely. Well, I think the intersection form, at least to us, wasn't obvious. The hard part is the sign. So we weren't sure for a long time if it was odd or even. And then we realized that actually we could understand the things from the picture well enough to just sufficing to give us a sort of parity of what we needed. And so the intersection form that comes is really the one associated to CP2 connected bar, CP2 bar.
Yeah. So there's no spectral sequences here that you're using? Ooh. Good for you guys.
Yeah. And maybe exactly different perspective might help in a more general sense.
I tried to figure out the intersection form in our example, and I couldn't.
Yeah, exactly.
I'm bad at
So we are
operator
just now looking at that example because I was curious if.
Yeah, I mean it's almost the same, but we get degenerate tetrahedra. It's a different cross
so
ratio.
what you get is that instead of getting tetrahedra at every point, in the case of SL3C. And the domain of discontinuity in the complex flags, what you get is at every point you get orthogonal geodesics. And so there the action instead of A4 is Z2 times Z2. But I think H2 becomes bigger. Yeah, so I think yeah, we don't know the intersection form either, but yeah, exactly. And I think in the reducible case is slightly harder, but in the reducible case, here you just get the whole PSL to C. You get no quotient, and okay, we are still finishing the calculation and try to understand how the degeneration goes. Yeah, maybe, yeah.
Maybe I missed it before, but how do you know the fiber can be smoothed out to an actual smooth fiber bundle?
How?
So this explicit.
Oh, why our projection is smooth?
Well, the explicit one is not, right?
The explicit one is not, but in order the intersection form, so these two are homotopic, and so for the intersection form you only care.
Where does the smooth one come from?
Oh, where it comes from our theorem.
Okay, so that's more mysterious.
Yeah, so from our theorem that it really comes from this barycentric, the barycenter of the Haar measure, and so is very abstract, and that's why it's hard to study the fiber in general. But exactly, so the luck is we built this non-smooth case, and yeah, but it will be interesting to see. That's why I was saying it will be interesting to see if this CP2 has a more geometrical meaning. Maybe, yeah, because it's not a, or it doesn't really seem a random for manifold. But anyway, this is just, yeah. Oh, yeah. Not, but because like they are both homotopic to the domain of discontinuity, because you have a projection into a simply connected space, so they are like in some sense, yes, it's yeah, it helps that, and so but yeah, other question. Okay, maybe I finish with a question. So as I was saying, at the beginning we were trying to go a different route, and we were trying to look at the sp4r orbit. This theorem is true in general for sp2 and r, but in the case of sp4, we have 3 open orbits. We have 1 closed orbit, and then we have this intermediate orbit. So it's really nice how this orbit comes. And so what you look at this space R0. So R0 is the space of Lagrangian, such that the dimension of the intersection of the Lagrangian intersected, omega intersected omega bar is 0. And so because our symplectic form defines a non-degenerate Hermitian form, then it makes sense to ask when these are 0 to split into the space where the Lagrangian has signature 2, 0, 1, 1, or 0, 2. And what is nice about this picture is that the conjugation gives you an involution where this H20 is sent into H02, H11 is preserved. This is where the closed orbit is, and this is H10. So so H10, what is H10? So you see that R1 fibers over the projective space, and the fiber really correspond to an H10. So, but the question is, first of all, so let's say now we have this nice picture of Lagrangian. Inside the Lagrangian space, we have the symmetric space of sp4r. Can this identification help understanding the quotient of the symmetric space by our group? With the work with other collaborators, Tengrin, Filippo, and Giuseppe, we define pleated surfaces in higher rank. Like, it will be interesting to see if we can find maybe, like, our definition is really in the boundary, but the question is, can we find geometric objects associated to these pleated surfaces? Maybe in order to understand better, like, can we characterize these spaces in terms now of how the roots, how these tetrahedra behave? Because this picture really works for Fuchsian, but you don't have a similar picture where, for example, you have quasi-Fuchsian space, but maybe there is. So if we define a representation, a characterization of these spaces in terms of how the roots behave, is like if they are on the limit set, or in how many ways outside of the limit set, that will help. Thank you very much.
Any other questions for Sara?
I'm going to save for after.
Guess we got them all.
Yes.
Okay.
Thank you.
Thanks, Sara.
Yeah, thank you so much.